Before we can solve a system of equations, we need to know exactly what a linear equation in two variables actually is. The rule is strictly mathematical. It's an equation with two unknowns, where the highest power of any variable is exactly 1. The standard form is ax plus by plus c equals 0. Substituting numbers gives valid equations, like 4m plus 3n minus 12 equals 0. But watch out, an exponent of 2 disqualifies it, and multiplying variables creates a combined degree of 2, crossing it off. To stay linear, an equation has to remain a simple additive path. The variables can't multiply by themselves, and they can't multiply by each other. Once we know how to identify a single linear equation, we can step up to simultaneous equations. This is where we analyze two of these linear equations at the exact same time. The objective here is precise. We need to find a single specific coordinate pair, an x and a y, that makes both of those equations mathematically true. Let's look at this example from the text showing method 1. We have a system stacked here. Equation 1 is 5x minus 3y equals 8, and equation 2 is 3x plus y equals 2. On its own, a single linear equation has an infinite number of possible solutions. But when you lock two independent linear equations together like this, they will usually share exactly one mathematical truth. To find that single truth, we can use the elimination strategy. The goal is to completely remove one variable so we can easily solve for the remaining one. Looking at our system, we hit an immediate obstacle. The numerical coefficients in front of the y variables don't match. We have a negative 3y on top and just a single positive y on the bottom. To fix this, we have to scale the entire second equation. We'll multiply the entire second equation by 3. Make sure you don't forget to multiply the constant on the right side of the equal sign. 3x plus y equals 2 transforms into 9x plus 3y equals 6. Now, let's stack our original first equation over this new scaled equation and add them together. Watch the y variables. Negative 3y and positive 3y cancel each other out completely. With y gone, we combine the remaining terms to get 14x equals 14, which simplifies perfectly to x equals 1. Here's where you take over. Pause the video, take that x equals 1, substitute it back into our original 3x plus y equals 2 equation, and solve for y yourself. Let's check your work. Replacing x with 1 gives us 3 times 1 plus y equals 2. That simplifies down to y equals negative 1. Our final coordinate pair is 1, negative 1. This algebraic manipulation allows us to temporarily unbalance and restack equations, letting the math do the heavy lifting to isolate that exact hidden coordinate. The algebra we just did has a physical, visual shape. Every linear equation forms a straight line, where every point along it is a valid solution. Let's try graphing a new equation. 2x minus y equals 4. To draw it accurately, we need to find some specific coordinate points. We can use the 0 trick to avoid messy fractions. First, plug in 0 for x. The 2x term completely vanishes, leaving negative y equals 4, which means y equals negative 4. Our first point is 0, negative 4. Now reverse the process. Plug in 0 for y. The y term drops out, leaving 2x equals 4. Divide by 2, and x equals 2. Our second point is 2, 0. When we translate these table values over to the Cartesian grid as plotted dots, we can draw a solid line straight through them. Strategically picking zeros creates a foolproof anchor. It lets us map out the infinite geometric possibilities of the equation without getting bogged down in complex arithmetic. If one line represents all the possible solutions to one equation, what does it mean when we graph two equations on the same board? This chart graphs x plus y equals 4 and 2x minus y equals 2. The single point where these lines crash is our simultaneous solution. Trace from the intersection down to 2 on the x-axis and across to 2 on the y-axis. This visual intersection proves the algebra we calculated earlier. The point 2, 2 is the one and only reality shared by both equations. To master these systems, keep this 4-step checklist in mind. Step 1. Verify the equation is linear by ensuring variables are exactly degree 1. Step 2. Apply the algebraic elimination method. Multiply to match your coefficients, then add or subtract to remove a variable. Step 3. When graphing, use the 0 trick in an XY table to find clean, easy points. And step 4. Rely on the graphical method to visually confirm your solution by finding the intersection of the two lines. Whether you manipulate numbers algebraically or draw lines geometrically, simultaneous equations are simply the search for a single perfect point of agreement.